I'd like to talk for just a minute about misleading graphs. So how graphs can be misleading or deceptive. So the textbook talks a little bit about this, but they could go into a lot more detail. So let me first talk about what a good graph is. So a good graph here should have the following qualities. Should have a descriptive title, should have labels on the axes, or if it's a pie graph on all the pieces of the pie. The axis scale should start at 0, or if there is a break, it should show the break. Axis should be uniformly scaled, and then pictographs have to have a key with a uniform picture size. So those are some general guidelines. Let me show you where things can go wrong and it can be deceptive. So the first problem that can happen is axis or scale manipulation. So look at this graph for a second. We've got vehicle sales listed in number in millions in 2010, 2011, and 2012. And we see in 2010 that there were 5 million vehicles sold. And in 2012, there were 8 million vehicles sold. However, look at this bar. It looks like it's 4 times as high as the bar for 2010. Well, in fact, it is. 1, 2, 3, 4. These are equally scaled, but notice it did not start at 0. So that's called a baseline change when that happens. And what it does is it makes this 8 million look like it's 4 times as big as 5 million. So it makes it look like there's a larger difference than there really is. So that's deceptive. Here's the same graph redrawn, but now the scale starts at 0. And you can see that while there is an increase from 2010 to 2011 to 12, it's not nearly as great as what it looks like here. It's not 4 times as many vehicles that were sold. So that's a baseline change. Let's look at another graph. This is a line graph, and we want to try and describe how this misrepresents the data. So we're looking at family size here, and they list 5 families. So this is a categorical variable. And then the size, notice here, doesn't start at 0, and then it goes up 2, 4, 8. So these scales are not equal. So this is a distance of 1, and then this is a difference of 2, and then this is a difference of 4. So this is an unequal scale. That's what's going on there. Unequal vertical scale. So if we were to redraw this graph with an equal vertical scale, it would look completely different. So if you, and then also here we did not start at 0. Okay, our start was not equal to 0. So we also had a baseline change. So those are things that are misrepresented there. How about pie graphs? So does this graph misrepresent the data? Well, the things that you want to check for in pie graphs are that everything adds up to 100%. And here we've got 39 plus 12 plus 20 plus 29. And if you add these guys up, let's see here, 29, 49, 59, 61. Yeah, these do actually add up to 100%. Okay, so that's good. That's the first thing to check. And then the next thing to look at, in addition to you have a key for what each piece of the graph is are these in the right proportion? So a quarter of a circle would be 25%. And look, this 20%, that's a little bit less than a quarter circle. Quarter circle would be about like this. And so that piece looks like it's about right. 20 is going to be a little bit less than twice 12. And you can see that 2 of these pieces don't quite fit into the 20, so that looks like that's appropriate size. And then, let's see, 3 times 12 would be 36, so we want to think, well, do 3 of those purple pieces fit into the 39? So if we did like 1, 2, 3, and a little bit left over, yeah. So that looks about right. And then the 29% we see that that's a little bit bigger than 1/4 of the circle. 1/4 of the circle would be here. And so it looks like all these pieces are appropriately sized. So this one looks good. So this one doesn't. Okay, this graph does not represent the data, misrepresent the data. Okay, so everything's good on this one. So that's an example of a good graph. However, when you're looking at circle graphs or bar graphs, you can run into three-dimensional effects. So notice here we've got the same graph and it's drawn two different ways. This is a three-dimensional version. This is a two-dimensional version. We are looking at the enrollment in thousands, student enrollment in thousands for 2010 through 2013. So notice that there's two dimensions in these bars. Well, actually three dimensions. You've got length and width and height. And notice that this little bar here, it looks like, it looks like a lot of those, little bars could fit into this big one, because the big bar looks like, if you look at this width and you look at this one, it looks like it's about twice as wide. And then the height here, right there, it looks like it's twice as tall, and then a little bit left over. And then the depth looks like it's about the same here. So it almost looks like, 4 of those smaller bars could fit into this bigger one, right? 4 of these little bars. And then some left over. But look, that lines up with 8. This one lines up with, looks like maybe 5. So 8 is looking like it's 4 times as big as 5. That's no good. So we get three-dimensional distortion there. So we're seeing that, this looks 4 times as big. Four times the size of 2010. Okay, but in the two-dimensional version, we don't see that over here. Okay, so you've got your 5,000, you got your 8,000. This is a little bit less than twice as much more. So this would definitely be a much more accurate way. Now notice that we didn't have a baseline change here, and the scale was even. So it did have those things going good for it, but we do have some distortion going on here, and that is a problem. You can have that same kind of distortion with pie graphs. So here's a three-dimensional version of this pie graph. Now this one is drawn well, and everything is proportionate, but if you look back over here, look at this 12% piece and what it takes up. It looks like that's about the same as the 19% piece, and it looks like the 19% piece is the same size or maybe bigger than the 28% piece. This doesn't look very big. It looks about the same size as this. Okay, and that's not the case. Look here, clearly the 28% piece is a lot bigger than the 19 and the 12. Okay, so notice we've got those distortionary effects going on here too. So we look at these two pieces and we think, what? Are those guys equal? So you want to just be aware of that when you're looking at graphical data. And then the last type of graph is a pictograph here. And so here's a pictograph looking at the number of people who own certain types of pets. And so this icon's where it's 50 people that have a dog, 50 people that have a cat, 50 people have a horse, and 50 people that have a fish. So what's wrong with this is that they didn't use a uniform icon. We need to use a uniform icon, because you look at this and look how tall this cat is compared to the horse. Did you know that cats were taller than horses? That's a revelation to me. And look at this fish. This is a pretty good sized fish, man. It's bigger than this horse. So that's sending some signals to your brain that can be deceptive. So you're looking at this and you're seeing 3 fish, and here you're seeing 3 horses, but these fish are bigger than the horses. So subconsciously that's making you think, oh well, there's more fish or more other pets here than there are horses because it takes up more area. And then here again, the cats look like it's a lot bigger in terms of area than it does the horses. Now one thing that they did do well is that all these icons, even though they're different, they do have the same width here. You go straight down. They do have the same width. So at least they did that part right. But that's also something that you want to be aware of. You want to use the same icon for each. They could, they could have used a key by color and then just used one pet to represent everything. That would have been a better way to do it. So those are some things that can go wrong with graphs, and hopefully that makes you a better consumer of graphical information.